This is my presentation of HyperStream DB, which is a serverless vector database. It is based off of the Iceberg format and contains additional sidecar indexes in order to speed up search for RAG applications. This is my own project that I have been working on for the last 4 months or so. It's very alpha, so if you encounter some bugs using it, just understand that this is literally the first time it's been put out for release in the last 2 days. Anyways, what makes HyperStream DB different? It is based on the Iceberg format. You can put it up in S3 or in Google Code Platform or Azure and still access your data and still be able to use it in a RAG application. Iceberg in and of itself doesn't really have indexes. It has different files for looking up things based on file statistics in order to find things, but it usually ends up doing scans of large amounts of data in order to find what you're looking for. And Iceberg, if you don't know, is built on top of Apache Parquet. So this is built on top of that as well. So it supports scalar, booleans, full vector search. It has its own SQL API based off of data fusion. So you can load tables up and do SQL queries on them and join with them. It has GPU acceleration for NVIDIA, Intel, AMD, and Apple Silicon. It supports ingesting via Python vector APIs. You can pass NumPy in, you can pass PyTorch in, you can pass PyArrow and Pandas data frames in. It has a Fluent Query API, which means you could chain methods onto each other like Pandas does in order to access your data. It'll do hybrid queries where you could actually query a scalar column and also query a vector column, so you could sort for the subsets that you're looking for before doing your vector search in order to speed things up. It has a native SQL syntax, like I said with Data Fusion. It does optimized joins via Data Fusion, and on the to-do is tying into both the Spark and Trino query engines. Right now it supports Iceberg version 2 and version 3 for the most part. Version 3 is fully supported. It's not supporting row lineage or default values. In version 2 they're not very well used, and it wasn't worth the effort to get the support in there for that. Now, as far as APIs go, you can load it up from an S3 endpoint, and you could access your data. You could set a sort order. You could partition it like Iceberg. You can read an Iceberg table, convert it by adding HyperStream DB indexes on top of your Iceberg table, so your data is not only accessible within the HyperStream DB API, but you could access it like a normal Iceberg table when you're using other applications that don't have the index support that is in here, because they're all sidecarred in and they don't affect the original Iceberg format. If you want to download it, I have the source code, which I'm reading off of right here off of GitHub. You can download it from source. I have it available as a crate in Rust because its underlying engine is Rust with a Python wrapper on it, and it's available in PyPy as well. All of these will be version 0.19 by the time this is posted up. It's building the final source release right now for distribution. It's, as I said before, it supports GPU acceleration. You get PG vector SQL compatibility, so when you're typing a SQL statement, you can do, L2 distances, cosine distances, Hamming distances, Jacquard, L1, you do inner products. So it supports the major distance operators that you would want in order to sort to get closest distance for your embedding. Basic use. You can load it in, as I said, via a data frame, or you could query it using the Fluent API, which is right here. I'll step through, we'll actually go through a notebook on this later. Rust also has that same Fluent API, so you could chain your methods on top of each other, or onto each other, I should say. It supports this auto detect is the documents that I did. This is not in here. I'll have an example showing you how to use it with Torch to get your GPU backend and use it for doing your searches. Let me see what else we have here. Just annoying. Join. Performance benchmarks. For a 768 dimension vector, runs in about 4,000, in just 4,000 rows a second on a Lenovo T480 i5. Very old machine. Not that fast. I have an Apple M4 Max. I can run it. I can ingest 17,000 rows a second, along with, while it's indexing. So it's pretty quick. It supports catalogs in Iceberg, so you can set it up to be like a traditional DB with using Nessie or Hive or one of the major Apache or even the Glue catalog in AWS in order to create more database-like applications where all your tables are registered and the locking is provided and you can get full ACID compliance like a database has with this package. And here's an example like how the sidecar files work. Like you have your main data here, then we'll have the scalar inverted file index. You'll also have centroids, and you'll also have your HNSW index as well in order to look up vector embeddings. Your main manifests are Avro, which is what Iceberg uses, and the metadata is all in JSON. Spark and Trino connectors are to come. This does work with Python. Let me see what else we have here. Project structure, roadmap. Okay, let me move into the actual tutorial. Let me start that up. All right, this is the actual notebook to show you how a HyperStream DB actually works, so you can see the code while it's executing. First, we need to import our modules. Here we use Torch to see if CUDA or MPS is available because it'll run on both. Right now it's detecting I'm on MPS engine since I'm on my Mac. Data preparation, we're first going to load up the AG News dataset from Hugging Face. And we're going to load up the first 500 rows, and we're going to generate embeddings from it using the All-Mini LM L6 V2 sentence transformer model. And there we go, loading up our data set. We got 500 records with the dimensions that this model puts out is 384 for the embeddings. Now for the table creation, right now this is all running on my desktop. It's serverless. I'm going to, for the sake of the demo, I'm going to use a temp file on my hard drive, but this would also work hitting S3. I've tested it using MinIO, so I know that it will work with S3, and have yet still to test it on Google Code Platform or Azure, but support for that should be coming. All right, so I actually loaded that data. Or I created the table, and I'm going to load the data in from the data frame, because beforehand I just put the data in a pandas data frame. I'm going to now load it into HyperStream DB. It has 3 indexes that I put on. If you've noticed from up here, up 4, it's the ID, category, text, and embedding. All right, so there's 4 of them. We're then going to test hybrid search performance, which is you could load up a scalar column. And for this, we're searching on the category column, which is a string, which will have the different news categories. And then it'll first filter on that, and then it'll do a vector search looking for the closest 3 embeddings. And I think the default is doing L2. So click on that, you can see then it'll give you your distance. So it's sorted by ascending order. Now, it also supports standard SQL because it uses data fusion. In order to get that, you must first register the data with data fusion. So you call the session, you first create a session, then you call session register on your table that you're going to load in. And from there, you're able to perform SQL queries. And here it is doing this PG vector syntax right here, giving us the different distance measures that it's sorting by. Now it also will give you vector aggregations. This will allow you to run centroids and other, whatever you want to do with that, which is interesting. Table maintenance. It does do merge on read, which supports the Iceberg spec. So it will create, if you delete something from the table, it doesn't actually delete your data. It puts a delete file in place, in which then you need to compact it in order for that to go away. So you compact and then you vacuum, and that will take any deletes out that you want to have removed in order to shrink your table down to a smaller size if it's getting too unruly. And that also helps because as you load data in with Iceberg, your data will start getting too sharded, and you'll have too many bits and pieces around. Doing a vacuum on it will clean it up and make it faster to go over. Anyways, we also support advanced partitioning, which is part of the Iceberg spec. You can specify what fields you want the partitioning to be on. You run it here, you can see it's going through and actually doing the partition to the Iceberg dataset portion of the code, and then it ends up redoing all of our indexes in order to support that partitioning. End to end, here's a RAG pipeline. I'm going to load the squad data set in. We're going to load it first into pandas, and then we're going to encode it with our Hugging Face model that I showed before. And we're going to load it into our HyperStream DB table, and we're going to just put indexes on the context and on the embedding columns. That's loaded up. Here you'll see we're going to ask HyperStream DB a question. We're going to use Grok using a Llama 3.370 billion parameter model. We'll embed our context from HyperStream into a pandas table, doing a vector filter on the embedding based on the query that we pass in, and we'll get an answer back out using only that context with the Llama model. So first we set up the function. Now here, where were the first Olympic Games? This was not in the data set. So you click this and tells you there's was not in the context, so that's good, and it's not hallucinating data that it doesn't see, it's only using the context. It said it didn't know about Super Bowl 50, so I asked it where it plays at. It's at Santa Clara, California, and that's it. I hope you enjoy my presentation.